All right, we're going to kick off our first session here with Geoff and Moustafa from the Microsoft Windows Defender antivirus research team. They're going to be talking about badly behaving scripts and how machine learning can be susceptible to attacks. First up, Geoff is, as I mentioned, an antivirus researcher specializing in machine learning to protect our customers from malware. He's passionate about reverse engineering, programming tools, fuzzing, and foosball. Moustafa is also on the antivirus research Windows Defender team. And before that, he spent a few years working in Office 365 ATP, also on reverse engineering malware. And he's got a master's and a PhD in cybersecurity from the University of Texas, San Antonio. And I'll just bring them up. Yeah, please give them a round of applause, and thank you.
Thank you.
Thank you. OK, hello, everyone. I'm Geoff, and this is Moustafa. And along with Bhavna, Jugal, and Andreas, we're from the Windows Defender AV team. So we work on Moustafa and I work on a team which is dedicated to using machine learning to protect our customers from malware attacks. Today, we're going to be talking to you about badly behaving scripts. This is malicious scripts. And we're going to talk about how AMSI script behavior instrumentation can be used along with machine learning to protect customers. Before we get started, we're going to talk a little bit about the malicious script threat landscape to give a bit of an overview of the context. So malicious scripts are used a lot by malware attackers at various stages of the attack chain. We see it used foremost a lot in social engineering attacks. Usually they send emails with malicious scripts attached to the emails and use social engineering lures to try to get the users to open the malicious attachments. We also see it used a lot as stages in attacks after they get a hold of getting execution on a workstation. For example, the rig exploit kit, as soon as it exploits an out-of-date Internet Explorer browser, the first thing it does is spin off a command shell, and it pipes a malicious JavaScript content to a file on disk and starts off a Windows script execution engine to run that script, which then acts as the downloader to download the real payload that they want to run on the customer's computer. It's used a lot in fileless attacks, both as stages in the attack to stay fileless, but also as persistence upon reboot through registry keys as well. As you know, malicious scripts are used a lot in advanced attacks as well. For example, there are entire pen test frameworks based on this, such as PowerSploit. And it's very popular as a lateral movement technique, both PowerShell directly as well as PowerShell invoking WMI for remote execution onto other machines on a network as well. Scripts, when they're executed by a user, they get hosted with script execution engines. These are Windows components. Like for example, if you were to run a JavaScript, a Visual Basic file, such as this case, it would get hosted using wscript.exe or cscript.exe. These are Windows components that are used for executing scripts on a machine. And it's the same for JavaScript. JavaScript gets hosted with the same two Windows components, wscript and cscript.exe. Another common file extension abused by attackers in social engineering campaigns is HTA files. These get hosted with a similar application, a similar script execution engine called mshta.exe. So social engineering often rely on these scripts. They usually pretend to be outstanding invoices. They might be missed package deliveries from FedEx, for example, or sometimes they pretend to be things like parking tickets, and they ask you to refer to the attachment to get more information. So if the user falls for these type of attacks, it usually runs packed and obfuscated script code, where these scripts are usually just downloaders. They usually just download a payload from the web, and then they execute the real payload that they want to infect on the machine. In this case, it led to ransomware, but of course, it's used to deliver all kinds of payloads. It's a very highly effective strategy. It's also used a lot with fileless attacks. Here's an example of persistence of how Koftor was carrying out their campaign. So at this time, Koftor was taking out malicious advertisements. So they were, the attackers took placing malicious advertisements with a legitimate advertising agency, and then these advertisements be hosted on many legitimate websites around the web. So if users visited one of these websites and happened to be served one of the bad advertisements, they'd be redirected to a fake Adobe Flash page. So this isn't a real Adobe Flash update page, but it would claim that your Adobe Flash Player is out of date, and for security reasons, you must update your Adobe Flash Player. So this would download an executable payload, and these executables would be trusted code-signed executables. They were defrauding the certificate authorities and getting code signing certificates issued to them in the names of illegitimate companies that they were impersonating. So they're using that to try to get through a lot of the browser-based reputation systems, which would be less likely to block these payloads as suspicious across the browsers. So if the user goes ahead and runs the executable payloads in these cases, it would set up its persistence through registry keys. It would store the Cofter malicious payload itself actually in a registry key, and they would set up an auto-executing auto-start registry key that would run every time the computer boots to reload it, to decrypt it from the other registry key and reload it, re-inject it into memory, staying off disk. Now, if you look closely up here, they use mshta.exe in this case as the executable script engine, and they got it to run a JavaScript command every time the computer boots. So this registry key doesn't normally execute every time the computer boots up. What they've done is added a new file extension handler, and they added a shell open verb handler that they've added with this registry key. So in order to complete the persistence upon reboot, what they would do is they would create an empty file with that file extension that they registered here, and they would just add an empty shortcut file pointing to the empty file in the user startup folder. So in this way, it actually did have a small file part, but harmless files that were associated with it, but all the malicious code was held within the registry keys. But it wasn't really necessary. They could have put these registry keys directly in a run key, for example. Then there'd be actually absolutely no file on disk in order for persistence. They were just doing this as a way to evade some of the AV vendors' detections of their app. OK, so malicious scripts are extremely easy for the attackers to obfuscate. Here are a few examples of what malicious JavaScript looks like. The techniques that they use to pack and obfuscate the JavaScript vary significantly, and it's constantly evolving over time to evade all of our antivirus signatures and techniques that we use to detect their packer technologies. So now here are three, which are different versions of Visual Basic script packed pretty similarly. So the problem is we need to be able to protect the very first customer from these malicious script attacks. When we look at all the malicious files that we see out there, 96% of files that we see are seen only by a single customer. These attacks are polymorphic. They don't hit a lot of customers with the same file. However, when this is normalized to look at the number of customers impacted by malware, it's 55% of our customers when they encounter malware. That malware is only seen by them as a single customer. So it still is a majority of our protection. It relies on being able to protect the very first customer from these attacks. So what the attackers are doing, especially with these social engineering script-based attacks, they're generating one version of the attack per customer that they email it to. They'd use the same packing code, generate many versions of it, and they would carry out a very large attack over a short time frame, going out in campaigns. So they would make sure it's not detected by all the AV vendors. Then they would send out, over a period of maybe half an hour, they might send out 10,000 or 20,000 or 30,000 emails to a large list of potential victims. And now the traditional AV signature way that antivirus products would handle this type of attack would be that we would collect a few of those scripts from the attack campaign. We would look at the script contents and try to write a regex-like pattern, which is able to cover all of the attacks as part of that campaign. So this is a very manual approach. It requires a person to collect the files, be able to write the regex-like signature, and then we need to be able to test that signature to make sure it's not going to false positive and deploy it to our customers around the world. It's a very slow process, and the problem is, meanwhile, all of the people receiving these emails are already opening the attachments, and the protection comes too late. So signature-based protection against especially these social engineering email campaigns are not an appropriate way to protect our customers. So machine learning is a very powerful tool we have, which is scalable to the number of campaigns that we see every day and every week. And it's also needed for a proactive defense against these types of attacks. OK, so now we're going to talk a little about AMSI. AMSI is a really cool Windows feature, which is also here to help us fight all of these malicious script attacks that we see. So AMSI stands for Anti-Malware Scan Interface. It's a standardized Windows interface, which allows any app, it doesn't just have to be a Microsoft Windows component, to create calls into the AMSI interface to request that content be scanned. So the thing is, a lot of Windows customers around the world use different AV products on their computers. It might not be that they're using Windows Defender AV on their computer. So this is a standardized interface where any app can call into the default installed AV on their computer, which doesn't have to be Windows Defender. It doesn't have to be our product. So it allows for scanning to request scanning of files, memory, streams, or URLs and IPs. So it's a pretty generic interface for any app developer to interface with whatever AV product is installed on the computer as a standardized interface. I encourage you to learn more if you're in the AV product industry or have an app where you might want to be calling the default installed AV product. We have a lot of great documentation available for the feature, and there's a lot of great GitHub examples on GitHub as well if you want to see some examples. OK, so Windows 10 has a lot of really cool script integrations with AMSI. So we're creating AMSI calls from a lot of our different scripting engines on Windows as Windows components. So at the Windows 10 launch with AMSI, we introduced PowerShell, VBScript, JScript, and UAC integrations. So let's have a quick look at how the PowerShell AMSI integration works. So PowerShell is open source. You can go look at all the source code on GitHub, so you can actually look at the implementation yourself. But if you look at the source code, you'll see prior to compiling any PowerShell code, it does a perform security check. And if you look at that, it does an AMSI call with the script contents. So PowerShell is generating a call to the default installed AV product with the contents of any PowerShell script before compilation. So if they run PowerShell.exe and then pass a base64 encoded string, which is the PowerShell script content on the command line to PowerShell, it will unpack it from base64 and then compile it. But just before compiling it, it's going to create an AMSI call, which contains the whole PowerShell script. And that's not it. Whenever it dynamically compiles any more PowerShell code, it'll be creating an AMSI call every time that compilation happens. So if that PowerShell script is now executing and it tries to load further PowerShell, it's going to have to compile that, and then that's going to be another AMSI call. So you're going to be able to see the decrypted PowerShell after it's unpacked a lot of times as well. OK, so if we look at how VBScript and the JScript AMSI integrations work, they're very similar. Prior to any execution of JScript or VBScript, you're going to get the script contents. So this includes if they try to use eval statements, executes, or maybe they use a function generator. It's going to pass all of the newly loaded JavaScript or VBScript code to the AMSI scanner to scan. So in this way, you get access to a lot of the unpacked underlying script contents. So this instrumentation is added to the Windows components, cscript.exe, wscript, mshda, and anything that uses JScript or VBScript.dll. So in 2017, with the Windows 10 Fall Creators Update, Windows launched another even better feature. So this introduced behavior instrumentation to the scripting engines. So in JavaScript and VBScript, we now get behavior logs of the scripts when they're actually executing on the customer's machine. So here's an example of what this behavior instrumentation looks like. The JScript and VBScript instrumentation logs all the COM interfaces. So we get access to all the COM functions as well as the parameters being logged by the script during execution. You may have heard about a week and a half ago, we actually launched Office 365 integration for Office macro content. So we also have behavior instrumentation logs being logged from our Office macros during execution as well. And I think for the Office 365 implementation, it's not just COM object interfaces. It's actually logging the behavior of selected Win32 APIs as well. For the future, there is a plan for a proposal for implementation in Python. So in the future, we might be able to get some Python AMSI interfaces. I think one that all of us security researchers have struggled with for a long time, being abused by malware authors, is AutoIt. I haven't heard of any integrations with AutoIt yet, but that would be a prime candidate for something that would work really well with the AMSI integration. So there's a lot of apps that call into AMSI currently. And there's a lot of security products which do support handling of these AMSI calls. From the public information that we have available, looks like at least the Windows Defender AV, ATP, and the selected vendors here are vendors that we see that publicly state that they support AMSI at least in some way. Though there's probably some more AV vendors beyond this list who we weren't able to discover if they do support it or not. Okay, so now we're going to talk a little bit more about how the AMSI behavior logging works, because that's really the focus of where we're doing our machine learning in our talk today. So the AMSI script instrumentation instruments the COM interfaces, and it logs the invocations. Now, every time a COM object function is used, it's not going to call into the AMSI scanner because that's too much of a performance cost. So instead, what it does is there's certain suspicious events, which is basically any execute type statement. That's when it sends the whole behavior log into the AMSI interface and waits for reply. So it prevents the script from continuing to execute until it gets a reply back from the anti-malware scanner. So these are the list of execute statements which are hooked. So if any of these statements, any of these ways to run a script, to carry out a run or execute from the instrumented script occurs, it will send the whole contents to the AV scanner to scan. So if the AV product comes back and decides it wants to block the script engine will not carry out the run or execute statement, and it will abort the execution of the script. And depending on which Windows script execution engine it was, you'll see a dialog like the following. And it'll say here you'll see the script contains a malicious content and was blocked by your security software. At the same time, with whatever AV product you have installed, they would probably throw a pop-up saying, hey, we detected Trojan XYZ on your computer at the same time. So you'd understand what the threat was. OK, so here are a couple examples of some malicious scripts, and we're going to see what the instrumented behavior of these malicious scripts looks like. This is a malicious JavaScript file. If you were to run this, you would have the following behavior logged by the behavior instrumentation. So in this case, the script executable the script is downloading a payload from a URL, then it's saving it to the disk, and then it's modifying the first few bytes of the file to make it an executable file. And then it goes ahead and tries to load it with run-dll32 to host the script. So right at this last line, this run command right here, it's going to pause execution of the script. It's going to hand this whole behavior log to the AV product installed. And if it decides to block it, it's not going to carry out that run action, and it's going to terminate the execution of the script. So here's another example. This is a VB script pack file. If you look at the instrumented behavior of this, you can see it's looking for a specific file on disk, and it looks like it didn't find the file, so it didn't continue executing the script. In this case, because there's no run statement or suspicious activity in the script, there would be no behavior call to the AMSI engine with this behavior log. However, we have all of the standard AMSI integrations where you would actually get this whole script content. Those calls you'd still get into the AMSI engine. You just would not get the behavior logs passed through. So if there's multiple run statements in a script, you're going to get one call for every run statement that it runs into, with more and more behavior logged in the script. OK, so now we're going to go over a little bit about Windows Defender Cloud ML and how we use it with this feature to do malware classification. OK, so this is the Windows Defender Cloud. On the left there, we've got the customer's machine. This is running our AV product. And the Windows Defender Cloud there are clusters of servers that we have located around the world so that the client is communicating to a cluster of servers pretty near it. So whenever the client scans a file, we actually don't normally send up the whole file contents to the cloud. Instead, what we do is we send up a featurization of the contents and description of the file. So this can include things such as the emulated behavior, such as the APIs called during emulation, things like fuzzy hashes, or we deploy a lot of specific ML feature vectors that we deploy per file type and per scenario. So all these features are sent up to our cloud, where we've got an array of heavy machine learning models that we run in parallel in real time. So we've got about 30 machine learning models here that run in parallel. And we also have ensembles that combine all the classifier scores to produce even further scores. So we combine this using decider rules and ranking logic to come up with a decision. And we combine this with offline deep learning models. So we've got deep learning models that actually, if we physically have the file, we've got full content deep learning models that process the file, but we also have deep learning models that process the behavior of the file when it explodes in a sandbox as well. And this gets combined with a lot of other very valuable information that we have, like how many other people in the world have seen the file, and how old is this file in the world. This is very valuable information when making a real decision about the file. And this gets combined with many different reputation sources from all across Microsoft, such as Office 365, SmartScreen, and many other sources to come up with a final decision, all in real time, of whether it's going to block that file or not. This is all real-time protection story. It gets back with the decision probably in less than 100 milliseconds usually. OK, so the problem is it's too costly to ask the cloud for every file that we encounter. It's too much of a performance impact on our customer's machine, and it's also costly in terms of cloud load. So what we do is we've got client machine learning models. These are lighter weight machine learning models. They're optimized to be able to run quickly and not use up too much memory or too much performance overhead on the customer's machine. And if these evaluate positive, we actually don't in most cases, we don't directly block on the client. Instead, what we do is we build a more detailed feature description of the content and then send that up to the cloud for the real decision. We also do this for any high-risk, low-frequency events. So anytime a file is downloaded from the web, any email attachments, or any scenario like that, like we have any reason to think it's suspicious, like it's packed or obfuscated, we'll always ask the cloud for a machine learning decision. So our Windows Defender Cloud handles about 4 million machine learning classifications a day, 4 million queries a day. And it's a very large number of classifications that we do. So now we're going to talk about how we build the AMSI behavior feature vectors for this protection scenario. So this is about the features that are sent from the client to the cloud for the classification. Specifically, these are the machine learning feature vectors that we build to cover specific scenarios. So we can't send the whole AMSI content to the cloud because there could be some PII reasons that we don't want to do that as well. So instead, what we do is we build a set of features to describe the content. So in order to build that feature vector, we based our features based on sandboxing logs to start with. So we use sandbox execution of a large set of known clean and malicious scripts to build the recorded AMSI behavior logs. And using these behavior logs, we added as features all of the COM objects referenced after normalizing for the version of the COM object, because our sandbox uses a different version of the COM objects than our customers will be. So that only adds 64 different COM objects which are referenced. And we do the same for all the COM functions which are referenced, which adds 193 features which describe all the functions which are used off of those COM objects. So now the more interesting part is how we describe the function arguments. We need to select featurizations of all the parameters passed into those functions to best describe the difference between the clean and malicious script behaviors. So for this, we do a strategy where we're selecting character engram features, because these are highly efficient with the way that our engine is able to featurize the content as well. So we use MapReduce because it's highly scalable for the initial feature reduction because we explode it into a very large number of feature candidates. So we take all the COM function arguments, then we evaluate all possible feature candidates by engramming the content of length 4 all the way up to length 14. This is a very large number of features, so which is why we needed to do the more MapReduce approach to the type of problem. So then, once we have a very large number of potential feature engram candidates, we apply a couple simple filters. First, we want any feature that we include to be able to generalize and describe more than one file, for example. So here we require that any feature candidate needs to span at least 10 different files to be considered as a feature candidate. And then finally, we have a distinctness of span requirement. We don't want to include 10,000 features that describe the same 10 files over and over again. So the distinctness of span requirement means that we're only willing to take at most 2 features that describe the exact same set of files because the features are perfectly parallel. So this gives us initial feature set candidate. And in this case, it gives us about 100,000 features to deploy. And this is too many features to deploy for performance reasons. So instead, to do the final feature down selection, we do a learner-based feature down selection. We take all of these 100,000 feature candidates, and we use the fast linear SASDCA classifier. This is a Microsoft researcher scalable improvement to the SDCA classifier. So it's an asynchronous one. It works really good for large scales of amount of data that we deal with. And we do the feature down selection through L1 feature regularization until we reduce it down to 300 distinct features. Now, these 300 distinct features aren't necessarily malicious features. They're the features which best describe the difference between the clean and malicious classes. So we have done some comparisons before using this learner-based feature down selection versus, for example, mutual information. When we've done at least the comparison versus mutual information, we found that the learner-based approach provided better classification using the resulting features. So that's why from previous experiments, we found that the learner-based was more effective, at least in mutual information. However, there might be other ways that might be better than learner-based. OK, so then we deploy. So in conclusion, we deployed a set of client features describing these behavior logs. They were targeting the COM object names that were referenced, the COM function names referenced, and a set of 300 n-gram features describing the function arguments. So here's a look at what the featurization looks like. Here's a malicious script. It describes all of the COM objects that the malicious script references. It describes all the COM object functions which are referenced by the script. And then all the n-grams are highlighted here that are matched. So these are the n-gram features matches that it describes when sending the featurization up to the cloud. And you can see it's latched onto some pretty interesting parts of the script. It's a decent description, but it can only go so far when we're only deploying actually 300 features here. OK, so now we just talked about sending features to the cloud. That is just our machine learning-driven features. So we have other generic features that still apply here, a lot of partial hash-based features. And we also have fuzzy hash-based features, which also play a role here. So this is just part of the features we have access to from the cloud to do the classification here. OK, so the problem is that these sandbox logs don't actually represent the behavior of these scripts in the wild. There are a couple of reasons for this. First of all, our sandbox environment is detected sometimes by these malicious scripts, and they don't exhibit the same behavior they would in the wild. And another huge problem that we have is enterprises use tons of custom scripts within their enterprises. They use all these VBS and JavaScript files a lot for custom enterprise scripts, believe it or not. And we don't have access to these files to get their behavior logs to train them as clean with our models. So it's a very challenging training scenario because of the huge variety of these scripts that we can't physically get a hold of to train against. So we just use the sandbox-based logs based on our known clean and malware files to produce the feature set that we deploy to the client. And we actually train our models based on the telemetry being sent from the client to the cloud, because that is the exact customer encounter with these malware and clean files. And this is how we train our cloud models as well as our client models, actually based on the in-the-wild behavior of these scripts instead of the sandbox logs. OK, so yeah, now I'm going to hand it off to Moustafa here to talk a little bit about how we approach the training label problem, as well as how we built our cloud classifiers.
Hello, everyone. Thank you, Geoff. So before I go into details of the experiment, I'd like to mention one of the challenges actually that we faced during that, which was to obtain a clean data set. So to solve that challenge, actually, we had to go through some assumptions. So the first assumption is that we use the enterprise machines. We assume that if a machine has no detection for 90 days in a row, and within those 90 days, we were successful to receive signals for 30 days, so we assume all AMSI files are actually not malicious. Also, one other assumption that was useful is that to look at the location of the file on disk. So enterprise script deployment, like for example, like CCM directory, which is usually used for system-wide installations. So we assume that files there are not actually malicious. Also, if it also belong to a library script like PowerShell, like Windows PowerShell directory, and like under System 32, so also we assume that. So we're able to have like a large set of files, and also we had to go through extensive manual analysis to verify those assumptions. On the client, we have deployed a lightweight model. For that, we use logistic regression that operates on features extracted by Ngram based on the contents of the file itself, plus also researcher signatures. On the cloud, we have also deployed a heavyweight model this time. And as Geoff also mentioned here, the relation between the client of the cloud, we have also a model on the cloud. So a question that you might be asking, if we have a model on the client, so why would we have another one on the cloud? There's actually several reasons behind that. First of all, we have access to global file history and information like number of machines, the first seen, date, the last seen, the geographical locations of the file, and so on, which is actually helpful as features also. We can extract more computationally expensive features, like features based on fuzzy hash. We have more business protection layers, reputation models, and also partner reputation. We can deploy also models that are expensive, like require more disk space or memory, and so on. And another important feature also is that we can also update the model on the cloud very quickly. And in fact, we update that actually every day. So rather than waiting for the user to update the EV on the machine. And another reason also is that the model on the cloud is away from the hands of adversaries, so they cannot reverse engineer it or cannot try to evade detection by using different features and so on. So for this experiment, we used around 70K samples, and we did also cross-validation with 50-50 split. We added a weight to maintain a ratio of 3:1 that actually clean to malware. So we started off with a large number of features that were actually coming from 3 sources: the partial hashes and AML signatures, plus researcher signatures, and also fuzzy hash. And in order to filter those, we had some requirements, like the minimum number of files that a feature span on, and also distinctness of that span. So we don't want the same features to span across the same files, like over and over again. So we ended up having around 42K feature sets. We did, as I mentioned, 2-fold cross validations. We started with the data, we split training and test and training. We get the average of that, and then we ended up with a final result. So one of the challenges also is choosing a learner. Which learner should we choose? And we have tried many, actually. We started off using linear models, logistic regression, average perceptron, linear SVM, SA-SDCA. The best of them was SA-SDCA. And then we tried also neural network. And at last, we used also tree-based models. Like GBM, boosted trees were actually the best. And like almost the same. So we choose a light GBM for the rest of the experiment. Light GBM is tree ensemble. It generated around 100 trees for the experiment. We chose here, for the sake of brevity here in the presentation, to show you around 16 tree. If we zoom on one of those, we'll have a tree something like this. Each node of that is actually a feature and a value of that feature. If it's actually below a threshold, it will go to look at another features and so on. If it's more than or less a threshold, it will actually go to another one. And the leaves are, the green is actually clean decision by the model, and the red is malware. So we wanted also to see the importance or the impact of features. So the contribution here is the importance of features. So if we use all the features, we get actually the best result, as you can see in the red line at the top. Right after that, we have the ML signatures and researcher signatures. Right after that, we got features based on fuzzy hash, and at the far end, we got the feature based off the partial hash. Another interesting thing also that we tried in the experiment is that we also tried the monotonic logistic regression. And to imagine the difference between the regular logistic regression and a monotonic one, imagine the regular one, it assigns a weight to a feature. If the feature is a malware, that's a plus. If it's clean, it's a minus. So the more clean feature is a plus to that weight of the feature, and so on. So if someone try to evade or work around the classifier, all they have to do to the malware is to add more of the clean feature. So that will actually increase the weight to bring it actually to clean decision. So monotonic model, on the other hand, it starts off assuming everything is actually clean. So if it's clean, if it's find a malware feature, it will add a weight. So the more malicious feature, it will add more weight. Now, the only choice for someone to try to evade detection is to remove malicious feature, which is actually hard. So looking at the performance of each, we ended up having almost the same result. So if we would go with any of them, we would actually go with a monotonic, of course. Yeah. So I think that actually brings the end of that experiment. I'll let Geoff wrap it up.
OK, thank you, Moustafa. So I'm just going to go over a quick summary of what we went over today. So Windows 10 has really cool AMSI integrations where the scripts are calling into the default installed AV product from several really cool places where we can do really good script machine learning-based protection. So there's the dynamic script content scans, where the AMSI contents are actually the script content itself, even dynamically during execution at certain points if they try to load further code script, for example. And then we also had the dynamic behavior scans. So here's a quick summary of the support we have in the latest Windows 10. So PowerShell, we have the dynamic script content of the AMSI calls. For VBScript and JavaScript, we have both the dynamic script content calls as well as the behavior AMSI calls. Now, when it comes to Office VBA macros, we've got the behavior AMSI calls, and it doesn't make a lot of sense, actually, to have the dynamic script content calls, because these all start from files on disk. When you're scanning the macro-enabled document, you already have access to all the macro content. So unlike the Visual Basic script, PowerShell, and JavaScript, where they can actually pass the whole script in on command line, there doesn't necessarily have to be a file associated with it. So security vendors can effectively use machine learning to protect their customers from it. At Windows Defender AV, we use paired client machine learning models, which are optimized for performance, paired with heavier cloud machine learning models. Our lightweight client models were logistic regression models. Our heavier ones in the cloud were tree ensembles. We found that our purpose-built ML feature vectors were among the most important feature that we had for the contribution, so it'd be really good to build purpose-built features to help support these scenarios. So this whole protection story really takes script protection level to the next level, and especially in response to all the fileless attacks that we see out there. So Windows Defender AV, we're the AV product on the endpoint, is just really part of a bigger story at Microsoft. Office 365 has lots of really amazing technologies where they're stopping all these social engineering attacks before they arrive in your inbox. They do tons of Sandbox explosions, and they've got their own machine learning models classifying all these scripts and so on. They do some really cool stuff over there. Also, in our EDR, in Windows Defender EDR scenario, that is our product which detects advanced attackers. We use AMSI integration and machine learning models on all the PowerShell scripts, and they use it to detect advanced adversaries in your network. So us at the AV product, we're just part of the story within Microsoft. There's a lot of really cool use of machine learning using AMSI feature, but also broadly targeting the malicious scripts all across Microsoft. OK, yeah, thank you. That's all we had to talk about today.
All right, we've got time for questions. We have mic runners on both sides, so just raise your hand and someone will come bring a mic over.
Thank you for the talk, gentlemen. A couple of questions. Can you actually comment on the requirements on the client ML in terms of latency? What's the effect on the client's machine when you have to run the ML?
In this specific scenario, we're running the client machine learning models only when we get an AMSI call with the behavior logs. So in our case, it's a very low overhead on the client because it's only going to run it when it gets an AMSI call from a script engine with a behavior log in there. So it's extremely low performance overhead.
And one more clarifying question on the numbers on Moustafa's session. You had 70K samples, you mentioned. And out of those, you got 42K features. All right, thank you.
Yep.
Question. Oh, one over here in the front row on the left here.
Yeah. So when you detect things in the wild, what do you do to respond to those things? Do you update client models so that they don't have to be sent to the server? Or do you like just add those file hashes to well-known malware, stuff like that?
Yeah, there's a lot of things we do when we detect malware. Like our client classifier models, which run on the client, I believe they're updated. I think they're once a day or once a week, so they update on a more slower cadence. Our cloud models update usually about once a day. As far as their signature release processes go, they would go through once a day. So if we're blocking a bunch of files, malicious scripts from the cloud, for example, we do have pipelines and processes where it's going to be automatically deployed as a signature to the client to make sure it doesn't even ask the cloud when our customers encounter the files. Does that answer your question? Okay.
Hello. Good presentation. So you mentioned that you have 100 milliseconds detection time. Did you ever measure overall end-to-end latency to submit everything and send back the result?
Yeah, so the 100 milliseconds is the end-to-end latency.
Thank you.
Yep.
Okay, we had another one on the front row over here.
Oh, yeah, one over there.
Hi, thank you. What is machine learning? No, that didn't land as well as I thought it would. So regarding clean machine state, I was curious how you guys handled SKU changes. Was that a one-time clean machine state that you guys used for the very initial training session, or do you guys change it for each SKU that comes out, as far as like Windows 7, 8, 10, 1803, et cetera?
So would you like to answer this? Or? Okay.
You can answer.
Yeah, so we don't do any specific training based on the SKU of their operating system. We consider all telemetry that's coming up, that's coming from AMSI feature, for example, in the training. But there are different requirements for different parts of the AMSI integrations. They're all included in different versions of Windows 10 releases. So that isn't a SKU that we account for. We just train all AMSI telemetry coming up, regardless of version. Yeah.
Okay, there's one over there.
Hi. If I'm writing a legitimate PowerShell script and I get flagged by AMSI, what is my recourse there to work around that hiccup?
So I think it depends on what antivirus security product it is, but if it's Windows Defender AV, you're going to see a threat detection pop up in the bottom right corner. There could be two different reasons the threat is being detected. So if it's, it could be a signature, like a signature-based delivery that is doing a detection on the behavior log, or it could be a cloud-delivered signature. But it'll show up in your antivirus product as a threat detection. There's a lot of different ways that you can do exclusions in the Windows Defender AV product. You can do exclusions by threat name, or by hash, or by threat ID, or I think you can do folder exceptions, but probably folder exceptions won't help with this scenario.
What if I wanted to distribute that PowerShell as well because it's a part of a product that I'm developing?
Yeah, I'd like to add also if it's.
Yeah, so to repeat what Holly just said, that was a good answer. Yeah, if it's a false positive, you should definitely report it to us. We have a portal where you can submit samples, and if you don't have a sample, you could just submit an arbitrary text file, and then you could explain the problem and detection name that you're facing, and we'll look into it and address the issues.
Okay, thank you.
But there are whitelisting strategies you can do too.
All right, and is that something that a malicious attacker could do, is follow up with the claim it's a false positive, and what's the security around that?
So those are manually reviewed. They're not automatically processed. So I've yet to see an attacker like deliberately submit false positives yet, but it is manually reviewed, so there won't be automatic.
All right, thank you.
Yep.
Yeah, and actually I have also a team also dedicated for that, or manually analyzing every submission on that, so no one can submit a malware and say it's FP or something.
Yeah.
So, yeah.
Great. Any other questions? All right. Well, Thank you guys very much.
you.
Great presentation, very interesting.
Thank you. Thank you, everyone.